Okay, so today, when I first gave the title for the presentation, it was around, I think, November or December was the title, like Deep Learning and Optimization. It was really difficult to decide exactly what the topic will be. So somehow I have specialized it to some extent, in which we'll use optimization for two different perspectives. First perspective is to analyze a block of layers in deep neural networks, and the second fresh approach would be use optimization for the reason they were supposed to be used for, which is minimizing functions. All right, so I'm a third-year PhD student in KAUST. Just to give you a perspective where KAUST is, it's in Saudi Arabia, right at the Red Sea. But I originally come from Jordan, which is very close to Saudi as well, but I was born and raised in Kuwait. So to me, this works fine because I can put all the countries in one figure. And these are some pictures from our group, and the ones labeled in red is my supervisor. One of them was roughly at around 4 a.m., maybe closer to ICV or CVPR deadline, if I remember correctly. All right, so we can get started now. All right, so I know that everyone is aware of deep learning. Many of you are already know more than I do. But one way I have to motivate this one way or another. So for the sake of the presentation, I would like to think about deep neural networks are nothing but stacked mathematical functions. And they are like reincarnation of what neural networks were, and they are excellent tools to understand data. And when I say data, now this is PDF, so there are unfortunately no videos, in which we'd like to give these images and videos to large deep neural networks and make high-level understanding from it, like segmentation, detection, etc. And in many cases, we would like to make decisions out of it, like playing games, Atari, chess, or board games. And apparently, we were very successful in doing so, and the progress just keeps going better and better. So one way to look at deep neural networks, which is basically a classification perspective, right? You have this massive network, you pass in my face, and gives you the classification score at the far right. And for the most part, this works very well, and you really don't care about what really happens behind this big machinery or a black box, so long it's doing its job nicely. The thing is that it seems that it's rather easy to fall in the trap of these adversarial attacks. So to some of you who are not familiar with this, basically it turns out that it's extremely simple to generate these small imperceptible noise, which people refer to as adversarial samples. You added it to the input image, which the network thinks that this is actually a panda with high confidence, and all of a sudden the network thinks that this is a gibbon, although to us there's absolutely no difference between the first and last image. And what's surprising to us is rather really simple to generate these adversarial attacks. In so many cases, it's as simple as taking the gradient of your loss with respect to the input parameters, do a single iteration of gradient ascent, and bam, you have your sample. And people have been doing this over and over again with extremely simple methods. And this sort of uncanny uncouth behavior sheds some light onto why we should maybe analyze these deep neural networks from a different perspective. Of course, more interesting works were basically that people were able to generate what they call adversarial attacks. That means regardless of what the input is, let's say we're working with VGG16, you take this exact sample, you add it to whatever image you want, and you will flip the classifier performance by high rates, regardless of what the input is. And so this is like input agnostic samples. But what turns out to be the case actually is you can take the same sample that is trained on AlexNet or VGG16 or whatever, you apply it to a different architecture and it will still fool the networks. There are apparently these weird directions that can fool arbitrary networks and with any input. So those like doubly agnostic samples. To understand these neural networks, the problem is that they come with all shapes and sizes, right? You have ResNet connections, dense connections, different activation functions, etc. That makes a holistic overall view to this problem rather difficult, if not possible at all. So in this presentation, I would like to basically go through a bottom-up approach in which we would like to take the common pieces into this architecture, which is, at least for the training part, it's made up of a dropout, then affine transformation, and another nonlinearity. Now, the affine could be any sort of affine, if you will, fully connected or convolutional layer, doesn't matter. We'd like to have a general abstraction of this notation. Nonlinearity, again, could be anything. And for the dropout, also you have this Bernoulli dropout, which is the standard ones used in the literature. And you also have additive dropout, which I don't know why do people call them dropout, but basically what people add Gaussian noise to the samples. So this is the bulk of the presentation for today. So we're going to analyze this block of layers through multiple sequence of works. And this will basically be the first part. But the second part is basically I'll be talking about a new algorithm that we have developed, where basically we'll do some optimization at the far end, where we'll basically be minimizing function rather than using it as a tool to understand neural networks. So let's start with the first part of the presentation. So I'd like to analyze a block of layers in deep neural networks from an optimization perspective. Okay, so the presentation will go as follows. I'll present first FFT LASSO, and then I'll jump to tensor convolutional sparse coding, which has nothing to do from the first perspective to anything with deep learning. But then at the far end, we will basically connect those two pieces together to build a formal model to describe this block of layers in deep neural networks. So you would be expecting not to see any deep models from now until we reach the last piece of puzzle. Okay, so for FFT LASSO, what we were interested in doing is basically solve this very simple problem, very well motivated, what referred to from different contexts as a lasso problem, which is basically would like to fit this data term with some prior on the solution to have a sparse solution. Now, to actually motivate this, it's very easy to do it from computer vision perspective. Specifically, if you ask someone from 10 years ago, they'll tell you, okay, this is very useful for face recognition. And to motivate this, basically what you do is you collect this massive dictionary of faces. Each block of columns, you vectorize these faces. Each block belongs to one particular face of a person, etc. You solve this, and you ask, I have a given B of some face, and I'd like to know to which face does it belong to. And you solve this problem, and basically you look at the density in C. C is supposed to be sparse, and the locations where the non-zero elements exist is more likely to be such that B belongs to that set. And the assumption is basically that for frontal faces, under different lighting conditions, these samples lie in the same manifold, in which one B is represented as a linear combinations with the faces that belong to the same object. So how would we solve such a problem? Well, there exist many ways to do it. What we'll be focusing on today is just first-order methods that are deterministic. So we're not talking about any stochastic algorithm for today during this part of the talk. And it turns out that one of the best problem solvers to solve this problem is actually to apply ADMM to the dual problem to this. So why is this the case? Well, if you apply ADMM to this problem directly, what really happens is that you're solving linear system in each iteration, and that linear system is as big as the number of columns you have in your problem, which is usually the matrix A is very, very fat, and you need to solve linear system of size n by n, where n is the number of columns in A. Now, if you generate the dual of this, what really happens is that dimensionality flips, and the number of variables are a function of the number of rows in A, in which, since A is oftentimes very, very fat, with very few number of rows, you end up actually solving linear systems of size n by m, and that gives you a significant speed up when you run this algorithm. Okay, so what we really want to do is to provide either a new algorithm or a new reformulation to this problem, in which it enjoys this linear convergence of ADMMs, very low computational complexity, and ideally it would be nice to distribute it over multiple GPUs. So how are we going to do this? Well, let's put down the lasso in perspective. So again, this is my dictionary A, has lots of columns, and this is the C that I'm optimizing for. I'll do something that doesn't make sense at the beginning, which is basically I'll take each one of these columns, and I'll generate a block out of it. And this block is very structured. It's a circulant block. If you see each one of these elements in circularly shifted. I'll do this for every single column in this matrix A. So if this matrix A is of size 4 pi n, where n is the number of columns, I end up with a matrix that's of size 4 pi for n. I replicated those columns. Now, in order to assure that both problems are exactly equivalent, what I'm going to do is simply add another set of constraints in order to enforce that the extra elements that appeared in C tilde that interact with those columns that I synthetically added to be exactly 0. In this way, I did not actually change the problem. The problems are both identical. If you solve this, you get the same solution as if you solve this. And I'm claiming that solving this is much better. although it is non-intuitive at all because the dimensionality has increased and the problem is now constrained. So let's look at this slightly more carefully. So this is the lifted lasso, let's call it. So C tilde is the bigger dimensional problem. Well, what really happens is because A tilde is made up of block circulant matrices, what really happens is that you can think about this as a set of convolutions. So a circular matrix times a vector is equivalent to doing convolution or correlation between that vector and the first column of that circular matrix. So you can think about this as a sum of convolution functions, and it is constraints. Now, to those of you who are familiar with convolutional sparse coding, well, this problem is in fact the inference step of convolutional sparse coding, which is something we'll talk about later. But the only difference here is that this problem is still constrained. So it is constrained convolutional sparse coding. Now, if you investigate these sparse codes slightly carefully, it turns out that it enforces your elements blocks in C to belong to the set of delta functions. So the first element is non-zero, all the rest are zeros. And if you do so, well, convolution with an impulse function, you're just actually scaling that vector, and this recovers back again the lasso problem. Great. So one observation, other than this is related to convolutional sparse coding, is that when you do lasso, you can think about this as a matrix vector multiplication with unstructured matrix A. So you can think about this as a fully connected layer for now. But it turns out, if you think about it carefully, is that somehow doing fully connected layer operation is equivalent to doing convolutions in higher dimensional spaces with respect to C tilde. And this will be very essential when we move on to the second piece of this puzzle. Okay, so what is FFT lasso? This is the original lasso problem. We're going to lift it and then generate the dual out of this problem exactly for the same reason you would do for the original problem, and you apply ADMM to the subproblem. Now, how is this useful by any means? Well, it turns out that you do not, well, you still need to solve a linear system, but it turns out your linear system is actually element-wise operation, and all the variables, you're updating the Fourier domain. So whenever you see a hat, that's the Fourier transform of that vector. And the complexity is as fast as you can compute Fourier transforms, which is n log n if the dimensionality of the vector is n. And all the operations here are element-wise, which tells you something about how easy it can be to parallelized. Okay, so what we do as well for the dual ascent step is we apply Nestrov's-like update to the dual variables in order to speed up the convergence. And this is the overall complexity. So if you apply the ADMM to the dual of lasso problem, you have a complexity of around m cubed, where m is the number of rows. But if you apply FFT lasso, the complexity around mn log m. So this means that the FFT lasso is extremely good for problems where the dimensionality is large for both dimensions. We have large number of columns and large number of rows at the same time, but not extremely large in one of the two dimensions. Okay, so we conduct some few experiments, of course. So whenever you see these lines below the horizontal line at 0, that means we're doing better. And we'll just keep it there. But just notice something, that there are dips which are improvement in performances precisely at powers of 2. And you would guess directly this is because we're using fast Fourier transforms and they're very nice at powers of 2. Okay, so basically just to hint here, the x-axis is the dimensionality of the problem, and this goes to fit it into GPUs almost about 10,000 by 10,000. But if we get our hands to much more bigger memory GPUs, to fit these 16,000 by 16,000 GPUs, we still observe improvement in performance. Okay, so now what about parallelism, right? So let's assume I have this big fat matrix A that cannot be fitted in any GPU, and perhaps not even on CPU memory, let's say. So, well, since we are doing everything element-wise operation, and the only relation between elements is when I take fast Fourier transforms along the column, well, I can just trivially split this matrix into arbitrary number of vertical splits, throw each piece on a GPU, and just communicate the Fourier transform for each piece and solve them on a local CPU. But what if this matrix A was just so massive that I can't even fit a single column on a GPU for whatever reason? Well, it turns out that you can actually also split it horizontally. And the means to do this is basically just to use a simple trick where you relate the Fourier transform of very long vector to the Fourier transform of the individual pieces of these vectors. And the problem would be solved. So now you can actually tackle problems that are large in both dimensions in a distributed fashion. Okay, so of course there are experiments of face recognition, but this is not the purpose of the talk, so we'll just skip those experiments for now. Okay, so of course you could use it for other non-smooth regularizer, perhaps, so long the regularizer is actually separable. The proximal operator probably would be also element-wise as well. You could also apply it to maybe linearly constrained problems because you're using ADMM as a base solver. Okay, so I've talked about convolutional sparse coding, and it's about time to actually represent this problem and see how those two pieces come together. All right, so the high-level ideas that I've given so far is that it seems that the lasso in an unstructured fashion is performing some form of fully connected layer, where this matrix is very unstructured. If the lasso connects somehow, again, this is very hand-wavy for now, fully connected layers to convolutional operators, but it has been shown several times by different groups that convolutional sparse coding relates very much to deep networks, and this means that we have to dwell into this CSC issue and see what's really happening here. All right, so what is convolutional sparse coding? It's basically based on the assumption how the images are actually formed in the human brain. And the idea is basically any given image X, and this is an assumption, any given image X can be represented as a sum of two pieces. Z's, which are very, very sparse, and set of dictionaries D's that are small in spatial dimension. So you have Z's as big as X's, very sparse, you convolve them, you aggregate the result to construct an image given X. Okay. So if this is how X's are formed, well, now what we can do is form an optimization problem, which is usually people refer as convolutional sparse coding. So let's see what this is actually telling us, right? So we'd like to train over a large number of training example in capital, but let's assume n capital is just one. And I have a single image I would like to reconstruct, which is Y, right? And the model says that any given image can be reconstructed as a sum of convolutions between set of sparse codes X's, which you see why you see the one norm here, and a set of dictionaries that are usually smaller in spatial size called D. And we're going to use K filters to reconstruct those. This is the prior term, and usually for scaling purposes, people bound the energy of those decays. Now the hope is basically if you have very large number of training examples in capital, you train this on a massive number of training data, you hope that you would learn dictionaries D or filters that are generic enough to reconstruct any naturally looking images. And then if you want to reconstruct new images that have not been seen in the training data, what you'll be doing is basically solve the same exact problem, but for a fixed D that you have learned from a massive data. And you do this inference step, and once you reconstruct this term, you have reconstructed your image. Now, why would you reconstruct an image that's already given to you? Well, basically, it's useful for in-painting, denoising sort of applications. Okay, so the first problem with this is that it was not clear to the community, well, how would you do this when you want to reconstruct tensor of data? So Y is not necessarily a 2D image, but tensor of data, or could be colored video, etc. And what we really want to do is to reformulate this somehow to allow for this higher dimensional representations. Well, what we'll do is I'll briefly discuss this multilinear algebra perspective of the tensor formulation. So this is a work by Misha in 2011. They introduced something called TSVD, and T stands for tensor. So this is tensor SVD. So it's called tensors because now your matrix A is, and this works only for third order tensors, and the order of the tensor is the number of indices you need to slice that tensor. So A and B are both third order tensor. And they propose this operator, let's call it TSVD for now, and this is defined in a very nice fashion. All it does is basically it says, take your matrix A, generate a matrix out of it, very structured matrix. Circ of A is a very well-structured matrix. Vectorize B in a specific fashion, and do a matrix vector multiplication out of this. And once you're done, fold everything back again into a tensor. This is all it says. Now, the way you would generate circ of A is basically, since A is n1, n2, and 3, you take those in 3 different slices and you stack them into a column. And once you do, you circularly shift those blocks. So that last block here appears on the top. Okay? Good. And it turns out that this matrix here, since it's very well structured, you can very efficiently blockwise diagonalize it. And the diagonalization is precisely doing tensor product between a normalized discrete Fourier transform and identity matrix. And this will give you the diagonal blocks of this matrix. Okay, great. So this is some other people's work. And what we really want to do is to extend these results to arbitrary order tensors, not only to third order tensor, to go back again to our convolutional sparse coding and reformulate it into this way. Okay. So, well, what you could do is just keep that notation and put HO and hope things work well. Well, this is not the point because we're not just changing notations. We have to define every one of these operators. And with some extra careful work, it turns out that the right unfold of the tensor will be something like this. So this is a visualization that hopefully gives you the right intuition. So let's assume for now I have fourth order tensor, and this could work with any order tensors. What you do is you start with the second, third dimension, or the last dimension, whatever you want. So we start here with N3. And all what you do is you unfold this around N3. So I have a vector tensor, and I have N3 of them. And once I'm done, I will start circularly shifting these pieces together to generate this tensor matrix. So this is not a matrix because I still have this green dimension. And once we do this, we repeat exactly the same process onto N4. And once you do, so this whole block is this what you see here in green, and I have N4 of them because I'm unfolding along N4 dimension. And once I do this, I circularly shift the block, I end up with a big, massive matrix that have very, very nice properties because it's structured on so many levels. Well, it turns out that this very well structured matrix can be very efficiently blockwise diagonalized again, which is something you can show. Is basically, the blockwise diagonalization looks something like this, which is equivalent to taking 2D Fourier transforms along these two dimensions, and then stack them into blockwise diagonalization. So these are your blockwise diagonalization. And this is what you would call a proposition for such a statement, is that if you take a tensor of arbitrary order tensor could be D dimensions, if you unfold it exactly the way we specified, it turns out that this can be diagonalized with a tensor product of discrete Fourier transforms, n minus one of them, and then an identity matrix here on the side. Okay, so let's go back again to our convolutional sparse coding. And well, it turns out that now you could let your Y to be arbitrary order tensor of data, colored video, if you will. And you can represent this tensor product precisely to describe these convolutions and aggregation across k number of filters. And what we really want to do is to solve this problem now. But before solving this, I just want to tell you that this is a very high abstraction to convolutional sparse coding and to standard dictionary learning approaches. Because it turns out if you set the dimensions at the right, correct way, this operator that we have introduced reduces to standard traditional CSC problem. So you'll cover that as a special case. Well, if you select the dimensions slightly more differently, this recovers again, this unfolding reduces to being an identity mapping, in which this would reduce to standard dictionary learning approaches, where people usually just say generic matrix D times X with no convolutions. Okay, so how are we going to solve this on the dictionaries and the sparse codes? Well, you do alternating optimization. You fix your dictionaries. So this is the overall problem that I'd like to solve. And basically, we fix the dictionaries. We assume I know D, and I solve for X's. And it turns out because this, because of the property of or tensor product of orthogonal matrices are still orthogonal, we could still use Parseval's theorem to actually replace this with a Fourier representation of the variables. And you can do everything in the Fourier domain completely to update this sparse coding step. Okay, how would you do the dictionary learning approach? The same idea, you could use the same exact trick. You still, of course, need to solve linear systems, but they are very small in the Fourier domain. And you could use, enforce the filter sizes in D to be actually smaller in spatial support. Okay, so again, you could use this to train on massive data. So these are like standard data sets people use. Okay, I can skip this for now. And the general conclusion of these experiments were basically that if you do our method where you construct tensor of data jointly, it is much, much better than the only approach at the time was possible, which is reconstructs each channel separately. So the SCSC here means single convolutional sparse coding. So you take your tensor of data and you construct each channel separately. The number of parameters in TCSC is much smaller because the sparse codes are shared across dictionaries. But also you can see, because we're looking at high-level correlations among the data, the dictionaries learned through our approach are also very generic and they don't overfit the problem. So if we take our dictionaries and construct each channel separately, we still actually perform better than using the dictionaries that are learned per channel, which indicates that usually this leads to overfitting issues in SCSC sort of approaches. Of course, now you can do other sort of applications that were not very clear before. We can do colored video reconstruction, where we have a video which is colored, so that's a 4D tensor of data. And you say, I have complete colored frames that are missing. And you train on those red frames, and hopefully you can recover those green frames, which is now possible with the method. Okay, so I don't want to really focus on the experiments of these methods, because these are just introductory to the important piece, which is deep layers as stochastic solvers. Okay, so again, so this is the top level idea. I would like to take this block and try to interpret it in an optimization perspective. But at the beginning, let me tell you what people usually do when they want to solve a given problem. So I come in, I say, I want to improve the state of the art on compressed sensing, in painting, denoising, whatever that is. I have one of two approaches. Approach number one is go to 10 years ago of knowledge, where we can nicely model the problem with data fitting term and lots of priors thrown into G of X, solve this, and hopefully I have some reconstructed image X that do very well. And to a certain extent, this was doing great because we have lots of human knowledge thrown into this. The other approach is say, okay, I don't care about all this stuff. I'll collect lots of data and train a massive network, and hopefully I'll learn everything I need from this data. And this obviously, everyone knows, performs much, much better than these classical approaches. But this is not a dichotomy of two pieces, because you can actually merge them together. And the way people actually do this is say, okay, since I know this models my problem very well, what I'm going to do is basically say, okay, let's say I want to solve this using some solver. ADMM is my personal favorite. And what you can do is look at one iteration step of the solver, whatever this algorithm is. You change ADMM with whatever you want. And you take your previous initialization, and you can form this operation. You could put them as a block of layers, block of operations, right? And then basically what you do next is to run this algorithm is all you need to do is replicate this block multiple times and feed in the output representations into the next block. So this looks like a recurrent neural network. So now you can think about running an algorithm on an objective function as nothing but a recurrent neural network. A very complicated block here incentivized by the algorithm that you choose to solve the problem, and you unroll it several times until you get the last intermediate representations. Now, this block is complicated, let's say, given the algorithm that you're using. But now what you can do is you say, well, why do we have to keep the parameters of each block the same? There's absolutely no reason for this, because obviously in the problem formulation, we have already put down lots of assumptions on what priors do we use. So what you can do is, well, learn this end to end. So you keep the structure as is, as it was told to you by the solvers that you have used. And now just let the parameters in each block be different and use a data-driven approach to learn this whole pipeline together. Okay, and this actually gives you much better performance than using just pure deep learning. But the problem with this is that this is all one-directional. So you say, I want to solve this problem. This is my optimization problem. I'll formulate a deep learning architecture out of this problem and outperform the state of the art, but the purpose here is different. What we want to do is go the other way around. We want to start with a pre-trained architecture and somehow relate it to a certain objective function. Is it possible that this network at intermediate level representations generating activations that are optimal in some sense, and are optimal with respect to a certain objective function? Well, let's start with a small, insightful example, okay? So we'll take this simple block, no convolution, simple, fully connected layer, no dropout, none of that. XL minus 1 is my previous activation, XL is my next activation, and we can write this simply as follows, where rho is my nonlinearity. So what I'm going to do now is tell you that let's optimize this function, f of x, g of x. The only assumption here is that this f of x can be written as a finite sum structure. Okay, now, this could be anything, really, but for the sake of this presentation for now, we'll assume that fx is quadratic. and we want to optimize for XL. Not here. We're assuming that the network parameters are given to you, and I want to generate output activations that are optimal with respect to this function. So I'm optimizing over XL. Previous activation are given to me. Network parameters are also given to me. Well, one way to solve this is you can use proximal gradient method, and this is how the update would look like. And L here is the optimal constant step size for such a method, which is maximum eigenvalue that's related to the parameters of this fully connected layer. Okay, so what I'm going to do is basically do this algorithm for a single iteration with zero initialization. And what really happens, I'll set L to 1 as well. With zero initialization, well, what really happens is that this solver for a single iteration looks awfully similar to what a feed-forward neural network actually is doing, in which the output activation here looks like a single iteration from proximal gradient method on a certain objective where we're optimizing over the output activations. Okay, in order to establish this connection very well, I have to show to you and convince you that there exist lots of functions g of x such that their proximal operator is in fact this nonlinearity that's commonly used in the literature. And we have put down this nice table here. So if you put down g of x, which is your prior on what you would like to see from your output activations, to be this non-negativity constraints. Well, this is clear that the proximal operator of this is nothing but a ReLU, which is very common in the literature. Okay, well, something more interesting, if you apply to this something like a squared SVM loss prior on the output activation, the proximal operator is a generalized leaky ReLU. And it's generalized because it has a parameter that controls the slope, and it has a parameter that controls the shift of that function. Well, if you use log barrier sort of assumptions on the priors on the output activation again, you get these very nice approximations to soft plus and 10H. Okay, that's good. So what did we establish so far? That you can construct several nonlinearities by changing your prior term on the output activations with different functions. And we have established this fully connected layer. We would like to abstract this and generalize it even more. I do not want to restrict this to fully connected layer, which is, for the most part, what you see in papers is when they do analysis, these are the results for fully connected, these are the results for convolutional layers. And I would like to abstract these notions and to figure out what is this optimal constant step size if I'm using a convolution layers here, and where does dropout have to do with any of this thing. So, unfortunately, this is not a PowerPoint presentation, but this is fairly known to everyone here. I want to highlight how convolution layers are not really trivial. So although they are linear operators, but there's something happening extra on top of the convolution, which is basically what you do is you take each one of these filters, you perform 2D convolutions, and once you're done, you aggregate these activations. So it's really very difficult to represent this as a single matrix vector multiplication because of all these operations. So it's not a circulant matrix, for sure not, because we're not only doing convolutions, but we're also doing this aggregation business. And of course, if you have also multiple filters, after you aggregate things, you'll get these multiple output filters. So we know it's a linear operator, and thus there must exist some big, massive matrix that represent this whole operation. And we really don't know what that matrix looked like. And even if we did, most probably we can't fit it in memory, let alone applying SVD on top of it. OK, so this is the first result here. And I'll just parse it really quickly for you by doing so. So what we're saying here is if I have a set of filters A that has N2 filters, WH are your spatial sizes, and N1 is the number of activations of those filters, or the number of filters in second dimension. And if the previous activations were also of spatial size W and H, and I have N1 of them, which is the standard setup in convolutional neural networks, where it turns out that this tensor product that we proposed before in CSC is precisely performing this convolutional layer operator, in which indeed it does perform 2D convolutions spatially and then aggregates those along N1. Okay, this is great, because now we can put down our objective function. So instead of this as being matrix vector multiplication, just like for simple quadratic, we can represent it with this high-order tensor product. Okay, so the next question is, how would we compute the optimal step size if this is my objective function? That would require us to diagonalize this operator. But as you all know already, that now we can use the properties of this operator to tell us something about computed the smoothness constant of this function, which looks something like this. It says basically look at the maximum among a set of eigenvalues, and each one of these eigenvalues is Fourier transforms of your filter. Something similar to what we have done before, but again, this is a set. Oh, sorry. Okay, so this was for the purpose to compute the optimal step size. Okay, well, to our surprise, so this work was presented in iClear, and to our surprise, there was a paper in iClear submitted at the same time from Google Brain. The title is precisely how to compute the singular values of convolutional layers. And to our surprise, they have the same exact result, but the analysis is very different. Ours was slightly easier just because we made this simple observation. So this is now for the first time, you have simple ways to actually compute the full singular values, or the maximum in our case, of convolutional operators, which was something not clearly known before. Okay, so where does dropout play a role into all of this? Well, it turns out, since this is the objective that the neural network are trying to approximate its optimal solution, it turns out if you run, instead of proximal gradient method on top of this, but if you run a stochastic proximal gradient method in which you sample this N1 function in mini-patch fashion, where the size of this mini-patch is highly related to your dropout, you recover again this feed-forward layer in neural networks. So what this says is as follows, extremely simple. It says, take this objective function, solve it for a single iteration, and this is exactly equivalent to doing a forward pass through a block of layers, which are composed of dropout, linearity, non-linearity, regardless of that linearity if it's fully connected or convolutions, because this reduces to standard fully connected layers under specific choice of dimensions. Well, this is some extra result that we could maybe just quickly highlight. If the dropout layers is actually additive, in which you add Gaussian noise before passing to the linearity and nonlinearity. Well, this turns out it's a special case of an algorithm which is twice stochastic, but it's also generalization to any variance-reduced type algorithm. Okay, so this is the big picture. Great. So the choice of the stochastic algorithm, or the choice of, if you will, deterministic algorithm of the mini-patch size is as big as N1, will play a role in what is the dropout layer that you're looking for. If the change in the prior term of the output activations play a role in the change of the proximal operator. Now, if you'd like to solve this, you can imagine this is as there is a feedback layer in here. It looks like a resonant connection to the other side. But in feed-forward network, we only have a single layer. We don't have this feed backwards. So the question is, how is this useful, these connections between those two pieces? Well, now what you can do is you can take one block of layers that you usually do feed-forward pass through them and replace it with a stochastic algorithm instead. The intuition is that if the network was originally trying to approximate the optimal solution to this objective very crudely by doing a single iteration, well, what could happen if we replace it with a recurrent solver or a recurrent neural network? So we have small experiments on very small architecture, but just tells you that you can actually improve the generalization performance. I would like to highlight that these standard deviations are not because we're running multiple trainings. These are actually the network is stochastic at inference time. And remember, we're running a stochastic block of layers every time we're doing a forward pass. You can do some more experiments on AlexNet, Cypher10, Cypher100. You can also do it on VGG16, on Cypher10 and Cypher100 again. And we also studied the correlation between what I just described earlier before, which is the number of the relation between how big is your mini-patch size and the relation with the dropout rate. And they seem very much related, in which decreasing the mini-patch size or increasing dropout will drop the performance in general, which what we expect because we established this connection, but the drop is much more graceful in terms of the mini-patch size. Okay, so I mean, I'll stop for this first part of the topic here, but I'd like to also highlight that we have lots of other works into this where we investigate the same exact block of layers, but from different tools. We have a work in CVPR from probabilistic perspective. I think we'll hear a similar talk very soon into propagating moments across architectures. We're investigating this from a tropical geometric perspective and an interval bound perspective, which is under submission for now. Okay, so let's jump into something else where we're going to use optimization for actually optimizing functions. And I'm going to present a recent algorithm that we have also developed very recently for derivative-free optimization with some applications to reinforcement learning and continuous control. So what do we want to do? I would like to optimize this function, f of x, under minimal amount of assumptions. So the function is smooth. I have quotations there, so you could will formally define what that is, and it's not necessarily convex. And the typical approach is there are multiple ways. You could say, okay, I'll do it in a zero-order fashion, first order. So zero-order fashion means I don't have access to gradient, and I cannot approximate them. Potentially, maybe you can, but you cannot use gradients explicitly. And the idea is very simple. Basically, you compute the objective function. You see if it decreases along a certain direction. If it decreases sufficiently enough, you say, okay, this is my next step. If it doesn't, you simply decrease your step size and you repeat again. So you're not using any gradient here. First order method, which is like a gradient descent, that's well known, or you could do Nestrov's-like acceleration, just like what you, well, in deep neural network, you use Boliak-like updates. Or you could use second order information. And for this part of the talk, we're focusing on applications where you cannot actually compute gradients. Okay, so because we're going to talk about convergence of such an algorithm, so let me tell you how people measure convergence. If the problem is convex, we'll refer to these, usually sometimes people refer them as Lyapunov functions. One way to measure is how far is my argument to my optimal solution x star, we'll call this AK, or in terms of function value, so we'll measure it in this sense, or you could say if the problem is non-convex, you say, okay, how small is the norm of my gradient? Now, if you're running a randomized algorithm or stochastic algorithm, if you run the algorithm for the same number of iteration at xk, well, obviously these xk's are random. So basically, you take just the expectation of this quantity, and you see how fast does it converge into this quantity. So just to give you a high-level idea of what the rates can look like, well, let's look at this. So we have been, I think, been talked about this before, which is subgradient-like methods. Subgradient methods have a square root in terms of the number of iterations. So this metric here, AK, which is how far I am from optimal or the norm for the gradient, depends on square root of iterations. So if I want to represent this as iteration, so if I want AKK to be less than or equal to epsilon, this is quadratic in epsilon. That means I will need at least this amount of iterations to reach epsilon precision, right? So of course, if you decrease epsilon more, basically this number of iterations increases quadratically. Now, if the problem is convex, you have that dependence on 1 over k. Of course, you'd expect some improvement. Now, if you do momentum, well, perhaps this is acceleration. Basically, you get the square root dependence on epsilon, so things are improving. And if you're working with a strongly convex function, you have this linear rate. So the error drops exponentially fast. You get this log square root of 1 over epsilon. So no one actually currently, at least stochastic optimization, are using around this location. And this is typically the rate you have for subgradient methods or on convex problems. Okay, so I'll just introduce really quickly some of the few definitions. What is convexity? Well, this is first order definition of convexity, and we're just saying if f is convex, I can always lower bound it with a linear line. If it's second order convexity, well, the Hessian of this is non-negative. Okay, that's easy. The strong convexity, which is what why I'm mentioning this, is precisely saying that the Hessian is greater than some constant lambda that is greater than 0. And instead of saying I can lower bound my convex function with a linear line, in fact, I can lower it with even something stronger, which is a quadratic function. And this is what strong convexity is actually doing here. So it's stronger, as the name would suggest. Another assumption, which is a gradient Lipschitz or smoothness, basically the same thing as strong convexity, but we're putting an upper bound on this Hessian, which is greater than L identity. And it says something like, okay, this is since the function is convex, I can lower bound it with some linear line, but I can also upper bound it with another quadratic from top. Now, what does the Hessian mean? It means that your gradients don't change much. This is when you say that the function is smooth, it means precisely that. The gradients don't change much, and the Hessian is somehow upper bounded. So let's go back again to our problem. We want to minimize this function f of x, and where f is smooth, just like what we defined in a moment ago. But I will assume I cannot compute gradients, or estimating them are extremely terrible and cannot be done, or very expensive, just simply do not exist. So before I present the algorithm, I'll just add one extra assumption, which is the same smoothness that we have talked before about. But it's a smoothness with, instead of having one L that upper bounds the whole quadratic function, it is with respect to Li in each coordinate. So instead of saying that the Hessian here, maybe I should have put it here, instead of saying the Hessian is bigger than one single L identity, I'm just saying it's with diagonal matrix with different LIs. So basically, what I had before implies smoothness. So this is nothing significant. Okay, so here is the algorithm. Extremely simple. Could not be, I think, simpler than that. I am going to select a random direction from whatever distribution you wish. Uniform, Gaussian, choose whatever you like. Compute your function at 3 different steps. Alpha xk, minus alpha xk, and wherever you were. And just take the minimum across these 3 values. And you already see that the function will never increase. And it has very well nice behavior. But what we'll do is we'll do something extra on top of this, is that we'll restrict the directions to a discrete set. So I'll assume instead of sampling from any direction, I'll assume from any discrete distribution across the set. E1 is a canonical basis. So this is 1, all zeros, then 0, 1, all zeros, etc. And this is not a restriction because we could have this any arbitrary set of vectors that span Rn because we can use this change of variables. So here is what the algorithm is actually doing. So if I am in 2D, I'm trying to minimize this quadratic. I have those 2 directions, 1, 0, and 0, 1. You simply choose one of them at random with these probabilities. So if you choose the first one, you'll take a step along this direction with a specific step size, or you take it with the 0, 1 with a different step size. So this is your set. You sample from it according to some probability law, and then you apply the algorithm and you repeat. So this is it. I will give you at the beginning of the algorithm some constants V's, and those probabilities that you will sample from. You'll select one of these n directions according to this probability law. I'll give you a formula for this alpha that is proportionate to 1 over VI's, those constants that will be given to you. You apply this step, you take that direction with plus and minus and compute wherever you are, and you take the minimum across those 3. So what we want to present here is the convergence rate of this algorithm. So let's look at this. It's extremely simple. All it says is that assumption was satisfied. My function f is smooth. This is all it says. Well, if you use a step size that is decreasing, as decreasing because k is a number of iterations, so as k increases, you're killing this step size. Well, if you run this, if you run the algorithm for this number of iteration, or at least this number of iteration, you're guaranteed to have the gradient less than this epsilon. And you can see now the dependence on epsilon is epsilon squared, which is what we'd expect for a non-convex problem. But what is nice about this is that the rate here is a function of those probabilities that we don't yet know, and a function of those VI's, in which what we can do is minimize this whole function in BI and VI jointly. Now, if you use constant step sizes, well, same thing would just apply. This is no longer a function of k, and this is the minimum number of iterations you need, at least, to get the norm of the gradient to be less than or equal to epsilon. And again, depends on epsilon squared. Now, if my function f is convex, we'll have some extra assumption that I can skip for now. You see that if you take this sort of step size, your rate actually improves. It's no longer 1 over epsilon, plus 1 over epsilon squared. It's now 1 over epsilon. And you guarantee something like this. So you know that you'll converge to your optimal solution when you run this algorithm sufficiently enough. If the function is strongly convex, you get this exponential rate of conversion. So it depends on log 1 over epsilon. And if you take this, of course, the step size, you guarantee such a this. So this is, think about this as a number of iterations that you'd like. So now we can take each one of these rates and optimize for PI's and VI's. And this is what you get. So let's say we're working with strongly convex functions. If I sample PI's proportionate to these LI's, well, you can get this particular rate. So let me give you an insight how gradient descent actually performs. So gradient descent on strongly convex function is this quantity here, right? If you use uniform sampling, that means you're sampling each one of these directions equally likely, you get this rate. You get this depends on n. And this is something expected because you're not even using gradients altogether. But if you're using this important sampling, you improve this NL to something like average. Instead of L max, you're using it in L average. And something similar for the other cases. So the question is where to get these LIs from? Well, I'll just motivate really quickly. If we're solving this for a massive A, which is maybe a million columns, if you will, and you want to run this algorithm without computing gradients, well, these LIs are precisely the energy of the data that you have. Well, if you run this, you perform significantly better than if you would sample in a uniform fashion. Okay, so basically here we have the dimensions. Here in you're increasing in the number of rows. Here you're increasing in the number of columns. We have experiments for much larger, around more than 1 million columns, I believe. Okay. Well, what happens if you have another smooth function, which is the soft squared SVM loss, for example? LIs are still your energy term, so you don't have to do anything extra on top of this. And there are, of course, experiments on this for rigid regression and on real data, which performs very nicely. Okay, so we'll want to use this for something useful in terms of application, where we'd like to, in reinforcement learning setting, you don't really have access to gradients, right? You usually have to push your agent in the simulator, observe the reward, and based on it, perform on it. So we'd like to see if we can run this algorithm. So the reinforcement learning is very suitable for this particular algorithm. And okay, so this is not a video, but basically the task here to learn a policy that you apply to these agents so that they run to the right as fast as possible. Okay, so how would we get these smoothness constants? We don't know them a priori. Well, if you run this algorithm for a specific number of iterations, you could approximate it with a family of parametric family of functions that are smooth and use a smoothness constant of these approximations. And this works very nicely in practice. So here we have multiple environments: swimmer, hopper, half cheetah, ant, and humanoid. And the numbers here is basically how many number of iterations you need to run your algorithm in order to reach a specific predefined threshold that is considered to be success for those relative tasks. We compare against state-of-the-art and policy gradient method and very recent method on derivative-free for reinforcement learning. We are doing better on lower dimensional problems, comparable or mid-dimensional problems, and slightly worse on large dimensional problems that are sometimes much worse. But we're always definitely better than just doing uniform sampling. Of course, these are some visualization, the same results but in plots, and how fast do we reach this threshold in the x-axis. Also, we have another version of this, so I'll conclude here, which came out also just the end of May. Where we develop the same algorithm, but we have both momentum and importance sampling at the same time. The results of these experiments outperform the remaining all the algorithms that we have shown before, but we'll keep that some later time. Okay, thank you very much.
Okay, thanks, Adel. Questions?
Thanks for a very inspiring talk, actually. So I have too many questions to ask now. Yeah. I would start with, I have too many, but maybe I'll ask two. The one question is there a connection between the first and second part of the talk?
No, absolutely not. Yeah.
Okay, the second question is more serious. For the second part, it looks like what you do, and you're doing I mean, your directions are direction of the variables, or this direction in which you generate the random vectors. Where you go, it looks like a stochastic gradient, stochastic block, or stochastic coordinate distance, whatever.
Well, so in the analysis, if you remember, I'm using canonical basis, so 1 all 0. So this is stochastic coordinate descent. But it's not gradient because we're not using gradients. However, as I mentioned, that we can just do a change of variables, and you just can take arbitrary directions. So these E1, E2. Yeah. So that's not, you cannot necessarily, do not have to necessarily see this as stochastic coordinate descent, because those directions could update all the parameters at once. So you could sample them from Gaussian, fix them, and then sample according to them.
Okay, thanks.
Thank you. Other questions?
Hey, thanks a lot for the talk. I was wondering, like this, the whole business with convolutional sparse coding and the dictionary learning was really similar to me of this non-negative matrix factorization stuff. Is it related, or like, what would you comment?
So you're asking whether or not convolutional sparse coding and non-negative matrix factorization are similar?
Yeah, like for example, in speech, there's this convolutional non-negative matrix factorization, which also finds like a set of filters that you would kind of convolve with a sparse code, and you sort of optimize for both filters. and the sparse code to represent your particular picture or like spectrogram or something. And it seems like, I mean, of course, if you never heard of it.
I'm familiar with those, but I'm just trying to think of whether or not at some level they meet, but I cannot see it from here. So I know that in there you would like to decompose your matrix into well, two positive matrices. One of them may be low rank and the other could be sparse, which is something people do in robust PCA, I believe. But I do not see how would the convolutions appear from such a decomposition. So if you do such a composition and you'd like to relate it back to convolutional sparse coding, I do not see immediately how they are related.
Yeah, oh, there's just a convolutional extension. I guess we could talk about it later. Yeah, thanks.
Thank you.
Thanks. Very last question, and then we go for coffee break. Okay.
Thank you for the talk, and I have a question about your assumption about L smoothness.
Yes.
So my question is, how realistic is this assumption? Because in real world situations, we can have adversarial-like data, in which I mean we cannot assume L smoothness, because this L parameter can be arbitrarily large in the small ball.
So I don't. It's extremely difficult to go for an assumption. I mean, to not make any assumptions at all. But remember, in a reinforcement learning setting, actually the functions are not smooth, right? The network could have these nonlinear activations. They are actually not differentiable altogether. But what really matters for us in terms of the smoothness is just to approximate the distribution of this important sampling business. And the way we did it there, because the function is not smooth, is we approximated while running the algorithm in an online fashion. You approximate the functions with a small neural network that use smooth activations, very crudely. The target is not to approximate the output of the function, but to approximate it crudely so that you have a better estimate of that distribution of LIs to get your probabilities PI and sample of them. And it works extremely well with that thing. And we did it with this other stuff with momentum as well, and it would work super well.
Okay, thanks again.